Hello friends, today we are going to see the trick by which we can solve phasor-based AC circuit sums very easily, very fastly. Okay, so before we move to the sum, let us see the basic concepts that are required to solve sum. Okay, so let's start with the series RLC circuit where you will find R, L, C all connected in series. Okay, so this is the voltage source which we have applied across this RLC. Okay, so this voltage source across this RLC combination will be VR plus JVL minus JVC. Okay, now you may be wondering how this equation come. Okay, so to understand this, let us find out the input impedance of this network. Okay, and to get the input impedance, we have to convert this circuit into the reactance form. Okay, so to do that, we are going to convert all elements into reactance form. R will be R only, L will be SL. Now you will substitute S to J omega, so it will be J omega L. Okay, similarly, C will be converted to 1 upon J omega C. Okay, now since this network is converted into reactance form, we can get the input impedance very easily. Okay, so this input impedance will be Z equals to R plus J omega L plus 1 upon J omega C. Okay, now if you multiply this equation with I, it will be IZ plus IR plus J I omega L plus 1 upon J omega C into I. Okay, now if we take J to numerator, we will get minus J I upon omega C. Okay, now if we try to simplify this I into Z, it will be Vs, right? Input current into input impedance, it will be Vs, right? Input voltage, so it will be Vs equals to Vr. Why? Because you can see I multiply by R, it will be Vr, right? Plus J I into omega L, I into reactance of inductor, it will be VL, right? I into R is V, right? So it will be JVL. Similarly, for capacitor, it will be minus JVC. Okay, the reactance of capacitance is 1 upon omega C, so it will be I into R, so it will be in voltage form. Okay, so minus JVC. So this is the equation that we are going to use. Okay, so this is Vs equals to VR plus JVL minus JVC. Okay, now if we simplify this equation, we will get VR plus J VL minus VC. Okay, basically we are clubbing real part and imaginary part separately, so we will get VR plus J VL minus VC. Okay, so this equation is converted to A plus JB form. Okay, now you can get magnitude and angle very easily. Okay, so magnitude of Vs will be under root of VR square, basically real part ka square plus imaginary part ka square. So here it will be VR square plus VL minus VC the whole square. Okay, similarly our angle will be tan inverse of imaginary part by real. Okay, so it will be tan inverse of VL minus VC upon VR. Okay, so this was the basic thing that you should know about series RLC circuit. Okay, similarly we have to understand the same concept for parallel RLC circuit also. Okay, so here you can see RLC all connected in parallel, and we have applied IS, basically input current, across this RLC parallel combination. Okay, so we will get IS equals to IR plus JIC minus JIL. Okay, so reason is you have to find out the admittance now. Okay, for parallel circuit you can find admittance very easily, and for series RLC circuit you can get impedance very easily. Okay, so in parallel we are finding admittance, so admittance will be 1 upon R. Basically you can say this is a impedance. Okay, so admittance will be 1 upon R plus 1 upon J omega L. Impedance is J omega L, so admittance will be 1 upon J omega L, right? Similarly for capacitor it will be 1 upon J omega C. Okay, so all are in admittance form. Okay, so this is our input admittance. Now if we multiply this complete equation by V, we will get Vy plus V by R minus J V by omega L plus J V omega C. Okay, so if you see carefully here, you have voltage upon impedance, right? Voltage into admittance is nothing but voltage upon impedance. Okay, so V by R is basically I, so all these terms are converted into I, so we will get IS, this is our input source, equals to IR, basically the current flowing through the resistor, minus J, you have kept J separately, so you have V upon omega L, which is nothing but IL plus JIC. Okay, so this is the equation that you should know about parallel RLC circuit. Okay, so if we simplify this equation, if we club real and imaginary parts separately, we will get IS equals to IR plus JIC minus IL. Okay, note this difference, here you were having VR plus J VL minus VC, here you have IS equals to IR plus JIC minus IL. Okay, now if you find out the magnitude, it will be mod of IS equals to under root of IR square plus IC minus IL the whole square. Okay, and if we calculate the angle, it will be tan inverse of IC minus IL by IR. Okay, now along with this you should know about power factor. In all series circuit, the power factor is given by cos pi, which is R by Z. Okay, this R is your resistance and this Z your input impedance. Okay, Here the minimum value of Z is R, okay, so we can say that R by R will be 1, okay, and if we increase the value of R, as we know that minimum value of impedance is R, okay, so if we increase our impedance greater than R, so this factor will be always less than equals to 1, okay, so we can say that power factor will be always less than equals to 1, okay. Now for parallel circuit like parallel RC, parallel RL, parallel RLC circuit, power factor is given by cos phi, which is equals to Z by R, okay. So note one thing, for parallel circuit this power factor is given by Z by R, for series circuit it was R by Z, okay. Here the maximum value of Z is R, okay, so if we decrease the value of Z, so this factor will be less than 1 only, okay. So we can say that power factor will always be less than equals to 1 whether it is for series or parallel circuit, okay. So this was the basic concept that you should know before you solve the sum of phasor circuit, okay. So let's start solving the sum, okay. So this is the first sum from EC 2005. The question is given that for the circuit shown in the figure, the instantaneous current I1 is, okay. So this is a circuit where you have to find out this I1, okay, and the options are present here, okay. Very first thing that you should do about phasors, that you should convert all the elements into its reactance forms, okay. So as you can see in this circuit, all the elements are already converted into reactance form, so we need not to do this step here, okay. So once you have converted your circuit into reactance form, then you have to start solving your circuit considering that your basic circuit, okay. So here in this circuit we have to get this I1, okay. So if we apply KCL here, you can see the current flowing here, it is phi angle of 0 degree ampere, okay. So here it will be minus phi angle of 0 minus I1 plus tan angle of 60 degree ampere, okay. So I have applied the KCL at this node. Here the current was phi angle 0 ampere, here the current was I1, and here the current was tan angle 60 degree ampere. So we get this equation, minus phi angle of 0 degree minus I1 plus tan angle of 60 degree equals to 0, okay. Now if we take I1 on one side and rest of the thing on the other side, we will get I1 equals to tan angle 60 degree minus phi angle of 0 degree, okay. Now this is in the form of polar, okay. If we have to convert this into exponential form, it will be 10 e raised to j60, okay. So basically magnitude into e raised to j angle, okay. So if we convert this into polar form, this will be 10 e raised to j60 minus phi e raised to j0 degree, okay. Now as we know, e raised to j theta is basically cos theta plus j sin theta, okay. So we can write this equation as 10 into cos 60 degree plus j sin 60 degree. Similarly for this it will be minus phi in the bracket of cos 0 plus j sin 0. Sin 0 is 0, so this term will be 0 only, okay. So here we will get 10 cos 60 degree is 1 by 2 plus j sin 60 degree is root 3 by 2 minus 5 into 1, it will be minus 5, okay. So here you can see 10 by 2 will be 5, so this 5 and minus 5 will get cancelled and we will have only this term 10 into j root 3 by 2, okay. So this is our I1 is equals to j 10 by 2 root 3, okay. Now if we write this into phasor form, it will be 10 by 2 root 3 angle of 90 degree, okay. As you can see here, all the options are written in phasor form, okay. So you have to convert your rectangular form to your phasor form, okay. So it will be 10 root 3 by 2 angle of 90 degree ampere, okay. So the correct option will be this A, okay. Now let's move on to the second sum. This second sum says that you have to find out the current I in the circuit, and note one thing, this is from EC 2010, okay. The circuit is here, the options are here, okay. So the very first step to solve this phasor based sum is you have to convert your circuit into reactance form, okay. So L will be converted to j omega L, C will be converted to 1 upon j omega C, R will be R only, okay. So if you observe this circuit carefully, here in the input voltage source it is given that you have a voltage of 20 angle of 0 degree and omega is mentioned, which is 10 raised to 3 radian per second, okay. We are going to use this omega to convert this L into its reactance. So L will be converted to j omega L, okay. So j into 20 into 10 raised to minus 3 into omega, okay. Omega is 10 raised to 3, okay. So if we convert this, it will be j omega L, j into 1000 into 20 into 10 raised to 3, so it will be j20, okay. So this L is converted to j omega L, which is j20, and this C will be 1 upon j omega C. J into 1000 into C is 50 into 10 raised to minus 6. If we take 10 raised to minus 6 in numerator, we will get 10 raised to 6 upon 50, okay. So if we simplify it, we will get minus j20, okay. So this capacitor is converted to minus j20 and this L is converted to j20, okay. Now you can see all the elements are converted into reactance form, so we can get our answer very easily. Okay, so now we have to consider this network as our basic network, and we have to apply KCL and KVL. Okay, so as we know, we have to get this I. Okay, so to get this I, we are going to apply the node. Okay, now this time we will consider the voltage at this node. Okay, so here we will have V1 minus 20 angle of 0 degree upon reactance. Okay, reactance is J20 plus V1 by 1 plus V1 upon minus J20. Okay, so this is what I have written here. Okay, now if we take V1 on one side, we will get V1 in bracket 1 upon J20 minus 1 upon J20. Okay, plus 1 is equals to this term. It will be 20 angle 0 upon J20. Okay, this minus will be converted to plus as we take this term to the other side. Okay, so now if you try to simplify it, you can see this term and this term will get cancelled, and you will have 1 into V1. So it will be V1 equals to this 20 gets cancelled. You will get 1 angle of minus 90 degree. As you can see, if we take J to numerator, you will have minus J. Okay, and minus J we can write in the form of angle, it will be minus 90 degree. Okay, so you get your V1 equals to 1 angle of minus 90 degree. Now this is not our answer. We have to find out this I, right? As you can see, we are asked to find out this I. So I will be this V1 by 1. Okay, so V1 by 1, it will be 1 angle minus 90 degree only. Okay, now if you see the option, you can see we have options in J form. Okay, so to convert this answer into J form, it will be minus 90 will be converted to minus J. Okay, so the answer is minus J 1 ampere. Okay, so you can see how easily you are solving AC circuit sums. Okay, now let's move ahead to the third sum. So this third sum is from EC 2012, and the sum is in the circuit shown below. The current through the inductor is, okay, basically we have to find out the current through this inductor. Okay, so IL we have to find out. Okay, and the options are present here. Okay, so if you see this circuit, you may be wondering this is very complex, but let me tell you, this is not complex as you think. Okay, we have to get this IL. Here you can see we have the current. Okay, the current through this branch is 1 angle 0 degree ampere. Okay, so if we apply KCL at this node, we have to find out the current IL. This is 1 ampere, so this current must be IL minus 1. As you can see, if we add IL minus 1 plus 1, it will be IL, right? So now we know this branch current, this branch current. Okay, now let's see whether we can apply KVL or not. Okay, so you can see we know this branch current, we know this resistance. Okay, here we don't know the current, here we don't know the current, here we know the voltage, here we know the voltage. Okay, now if we apply KVL like this, okay, in this bigger mesh, we will get IL J1 ohm minus 1 angle of 0 degree plus 1 angle of 0 degree plus IL minus 1. Okay, so this is what I have written here, minus 1 angle of 0 degree plus 1 angle of 0 degree 1 into IL minus 1 plus J into 1 into IL. Okay, so this is our first equation. Now if we try to simplify it, if we try to get IL on one side, we will get IL 1 plus J. Okay, and here you can see this term got cancelled, and we have only this. Okay, so if we take on other side, it will be equals to 1. Okay, so we will get IL equals to 1 upon 1 plus J ampere. Okay, so this is the answer. Now if you compare with the option, you can see this C is the correct answer. Okay, so from this sum, what you get, the circuit may be complex, but it is not the case that always your solution will be complex. Okay, so it's on you how you use KCL and KVL to get your answer. Okay, now let's move ahead to the fourth sum. This sum is from AC 2015. The question is the voltage VC across the capacitor in volts in the network shown is. Okay, now if you see this network here, you have a series RLC circuit. Okay, where you have this VS, this is a VR, VL, and you have to find out this capacitor voltage. Okay, as we have seen in the basic concepts, we are going to use the same equation here. Okay, as we have seen, VS is VR plus JBL minus JVC. Okay, note one thing, this is not the resistive network. Okay, where you will find the sum of all the voltage to be 100 volt. Okay, most of the students do a mistake where they try to make this capacitor voltage such that they will get 100 volt. Okay, and they end up with 80 plus 40 is 120. Okay, so they end up with minus 20 volt as their answer. Okay, but note one thing, this is not your resistive network, this is a complex network. Okay, so for that you have to use this equation where you will have Vs equals to Vr plus JVL minus JVC. Okay, now if we club real and imaginary part, we'll get Vr plus JVL minus VC. Okay, so our magnitude will be Vs equals to under root of Vr square plus VL minus VC the whole square. Okay, Vr is 80, so it will be 80 ka square, plus VL is 40, so it will be 40 minus VC the square. Okay, here we have Vs as 100 volt. Okay, so we have to make LHS equals to RHS. Okay, so for that here you can see 80 ka square, it will be 6400. Okay, and to get this 100 we should get this term as 10,000. Okay, so here we have 6,400, so this term must be 3600. Okay, such that we will get 10,000, and 10,000 ka under root is 100, right? So 40 minus VC the whole square must be equals to 3600, right? So if we take the under root, we will get 40 minus VC is equals to plus minus 60. Now if we solve this, we will get VC is equals to 100 volt and minus 20 volt. Okay, out of this we have to get one answer. Okay, so let me tell you, VR, VL, VC, all these terms are positive real number. Okay, so the correct answer will be VC is equals to 100 volt and not minus 20 volt. Okay, so note this step, you have to take VC, VR, VL all positive real number. Okay, so our correct answer will be VC is equals to 100 volt. Okay, now let's move on to the last sum. This sum is from AC 2017. The question is the positive angular frequency omega in radians per second at which the magnitude of the phase difference between the voltage V1 and V2 equals to pi by 4 radians. Okay, so here we have to calculate omega, and we are given with that the angle between V1 and V2 is pi by 4. Okay, so here also we will use the same procedure, that first we will convert all the elements into its reactance form. Okay, so we will get this circuit. Here you can see 100 cos omega t, this is your input, 1 ohm, j omega 1. Okay, so if you observe this circuit carefully, here you can see your input voltage is 100 cos omega t. Okay, which is a sinusoidal input. Okay, so it means this sum is of sinusoidal state analysis. Okay, if you have to do this sum by phasor, you have to convert this 100 cos omega t into 100 angle of 0, and then use the same procedure that I have taught you in the above sum. Okay, but let me tell you, by this you will make your sum very complex. Okay, so it's better that whenever you get 100 cos omega t, basically whenever you get a sinusoidal input, you use your sinusoidal state analysis steps. Okay, so the first step was that you have to keep your input and output as it is. Okay, we will keep input and output as it is. Okay, we will convert all the elements to its reactance form. Okay, that we have done in the circuit itself. Okay, now we have to consider this circuit as our basic network, and we have to use KVL KCL to solve this sum. Okay, so here you can see we have to get this V1 and V2. Okay, so for V1 we will use the voltage divider rule. Okay, so our V1 will be 1 upon 1 plus j omega plus 1. Okay, basically this resistance upon this resistance plus this. Okay, so you will have 1 upon 2 plus j omega into your input. Okay, this is your input, 100 cos omega t. Now if we simplify this, if we take magnitude and angle of this, it will be 1 upon under root of real part ka square, it will be 4, plus imaginary part ka square, it will be omega square, angle of tan inverse of omega by 2. As you can see, imaginary is this, real is this. Okay, so angle will be tan inverse of omega by 2. Now as we have seen in the sinusoidal state analysis video, always we have to add this angle into our input. Okay, and we will multiply our magnitude with the magnitude of our input. Okay, so our total magnitude will be 100 upon under root of 4 plus omega square cos omega t, and if this angle goes in numerator, it will be minus tan inverse of omega by 2. So if we add that, we will get cos omega t minus tan inverse of omega by 2. Okay, so this is our V1. Okay, now similarly if we calculate for V2, V2 will be 1 plus j omega upon total reactance, so it will be 1 plus j omega plus 1, so 2 plus j omega into input. Okay, so if we take magnitude and angle, it will be under root of 1 plus omega square, and angle it will be angle of tan inverse of omega by 1. Okay, imaginary is omega, real part is 1. Okay, so it will be tan inverse of omega, and for this denominator it will be under root of 4 plus omega square, angle tan inverse of omega by 2. Okay, now if we take this angle into numerator, it will be minus tan inverse of omega by 2. Okay, and if we add both this term into this omega t, it will be magnitude into 100 cos omega t plus tan inverse of omega minus tan inverse of omega by 2. Okay, so here you can see this is our V2, this is our V1. Now in the question it is mentioned that the phase difference between voltage V1 and V2 is equals to pi by 4. Okay, so if we take angle of V2 first, then angle of V1, so it will be tan inverse of omega minus tan inverse of omega by 2 minus of minus tan inverse of omega t, it will be plus tan inverse of omega by 2, right? So this tan inverse of omega by 2, this minus tan inverse of omega by 2 will get cancelled and we will remain with tan inverse of omega. Okay, similarly if we take angle of v1 first then v2, okay, basically angle of v1 minus angle of v2, so it will be minus tan inverse of omega by 2. Okay, here I have taken angle of v1 minus angle of v2. Okay, so here it will be minus tan inverse of omega by 2, then here we have plus, so minus angle of V2 will be minus tan inverse of omega, then minus of minus it will be plus tan inverse of omega by 2. Okay, so this tan inverse of omega by 2 minus tan inverse of omega by 2 cancel and we will get minus tan inverse of omega. Okay, mod of minus it will be positive, so we will get tan inverse of omega equals to pi by 4. Okay, now if we take tan inverse on this side, we will get omega is equals to 10 pi by 4, right? 10 pi by 4 is 1 radian per second. Okay, so our omega will be 1 radian per second. Okay, so the answer for this question is 1 radian per second. Okay, so once again let us see this question. Here in this question the input was cos omega t, basically the sinusoidal form. Okay, so we have used our sinusoidal state analysis wala step. Okay, first step was not to touch this, not to touch this. Okay, then we have converted all the elements into reactance form. Okay, then we have calculated v1 v2. Okay, and then using this statement angle of v1 minus angle of v2 or angle of v2 minus angle of v1, we have seen both the things and we have got the same answer. Okay, that was tan inverse of omega, as if we take the mod we will get tan inverse of omega only. Okay, and then we have got our omega as our 1 radian per second. Okay, so this was all about our phasor sums. Okay, so we have seen all the steps that we have to follow, we have seen the concepts that we have to follow. Okay, so that's it for today. Thank you guys.